All right, so now I want to take a second and discuss sort of some synthesis strategies or some multi-step, specifically multi-step synthesis strategies. One thing I'll say is there's no like one size fits all approach to these multi-step synthesis problems. They are the bane of every organic chemistry student's existence because they require a real mastery of all the different reactions covered. And we've covered about 30 different reactions, right? So from a memorization standpoint, that's just too much. Luckily, with practice, you'll start to see patterns. You'll be able to they'll be able to sort of categorize them, right? Like hydrogenation of alkenes versus alkynes, hydrohalogenation of alkenes versus alkynes. There's certain like patterns that you can spot. Nonetheless, it really requires you to sort of have a good understanding and a good memory of all the reactions that we've covered, right? Because every reaction that we've covered is sitting currently in your synthesis toolbox. And for any multi-step reaction, what you're going to do is look through that toolbox and figure out, does this work, does this work, okay? So as much as I would like to say that I have like this silver bullet way to approach it, it's kind of not that straightforward. But we can go through and sort of categorize some things that we've done thus far. So first of all, changing substituents. One of the first things we learned about are these substitution reactions. And they're a great way to change a substituent that's on an alkyl chain, right? So starting out, and again, the most powerful starting material that we know how to work with is an alkyl halide, all right? And we know how to generate them as well from alkenes and alkynes. So that's part of what makes them so key. But they're really central, kind of a linchpin in our whole synthesis strategy, okay? But first thing is changing those substituents through substitution reactions, right? And we've learned, it's different for secondary and primary alkyl halides, tertiary alkyl halides. There's all these considerations that go into it. But if you're trying to just swap out a halogen for an alcohol group, for example, these substitution reactions are how you're going to do it. Remember, now we have this new addition to our nucleophile like list here, which is this acetylate ion. And that's so key because it allows us to grow our carbon-carbon chain. Right, so previously we could have swapped out a halogen for an alcohol or a halogen for an amine or something like that. Now we can actually grow our carbon-carbon chain as well. And of course, you can take this triple bond and do other reactions with it, right? I mean, that's part of what makes this multi-step synthesis so crazy is there are many different avenues that you can go down. Another thing that we did in multi-step synthesis is the idea of changing the position of a leaving group, okay? So you got a lot of practice with this with last week's challenge problem, but maybe it wasn't necessarily obvious the pattern here, which is you're kind of always doing the same thing, which is first on elimination, followed then by an addition, right? The idea was you got to get rid of that leaving group first, create an alkene, and then from there you can do stuff to that alkene in terms of an addition of a new product, right? So this way, in this particular one here, we're going from a less highly substituted to a more highly substituted. So first we have to do an elimination where we form a double bond between the two. So this would be using something like just some strong base. You want it to be small though, not something that's big and bulky that will give you the Hoffman product. And then from here, you're going to do an addition where it's going to be on the more highly substituted carbon. So you're not going to want to use peroxide or anything like that. It's just going to be the standard hydrohalogenation reaction. Okay, but we could also go the other direction as well. And it's a good idea to practice that, right? How would we go the opposite way? A lot of these, you can get creative and start asking yourself, well, what if I did this? Well, what if I did this? That's a great way to explore these reactions and the different possibilities, okay? But this is when you're swapping a leaving group. You're going to be doing first an elimination and then an addition. And then we can do sort of the opposite, which is to change the position of a pi bond, where here first what we're going to do is an addition followed then by an elimination, right? So our addition, we'll put a new halogen in there, and then we can do an elimination in order to get our double bond back. So here, if I wanted to do an addition, I'd have to first do it'd have to be the anti-Markovnikov. So I would actually have to add HBr in the presence of peroxide, getting it on the less highly substituted carbon. And then I'm going to do an elimination, but I want it to form a terminal alkene. So that means I'm going to have to use something like tert butoxide, right? Something that would give me that Hoffman product, or another way of saying you have elimination on the less highly substituted carbon. Okay. So now in this chapter, we have a few other, a few additional things. So first of all, if you think the reduction and hydrogenation chapter, we have a bunch of different ways of going the reduced direction, going in this direction here. We can either go from alkynes to alkenes. That's using Lindlar, or you have this sodium in really cold ammonia. Or an alkene to an alkane, and we can do that through that catalytic hydrogenation. If we want to skip directly from an alkyne to an alkane, we can do that as well with catalytic hydrogenation, right? But I think almost more importantly is this idea that we know how to go the other way too, right? We know how to go from an alkene to an alkyne. And that opens up a lot of possibilities, and back and forth, right? You could circle around. And remember, how we do that is to first create that dihalide, right? So by doing a halogenation of an alkene, we create a dihalide, and then we can treat that with an excess of strong base, and we get our alkyne. Notice here, I'd have to add water because it's a terminal alkyne. Well, it's terminal on both ends, but the bottom line is that I have to make sure to put those hydrogens there as opposed to creating that acetylide ion. All right, so not only do we have a way of jumping sort of in this reduced direction here, we also have a way starting with an alkene to go to an alkyne. Notice we don't have anything to do starting with an alkane, right? Just a completely naked alkane. When we get to chapter 10, we will see things that we can do using radical reactions, but for right now, this path is kind of cut off for us. Okay, which is just a good thing to keep in mind. One other thing is that I think if you haven't sufficiently practiced, everything seems infinite. It seems like there are a billion different reactions and everything like that. The more and more practice you do, the more you'll realize that we've kind of only covered a small subset of things. And to the extent that you understand the subset that's covered, that will benefit you, right? Because if you look at it, it's just like it could be anything. Well, you're not going to be able to start off the problem very easily, right? So I just wanted to do an example here to kind of walk you through what my mindset would be. And again, unfortunately, it's going to be almost unique to every new problem. So I'm not going to guarantee that this strategy is going to work everywhere. But most importantly, I think just to see me going through my logic will be helpful, okay? So let's say that we had this synthesis here, and I said that this is your only source of carbon can be from this molecule here. So can you name this guy? So this would be propyline. You might be tempted to call it one propyline, but since there's no such thing as two propyline, we can just call it propyline. But I'm going to say that this can be your only source of carbon, and I want you to create hexane from it. Well, hexane's obviously got more carbons than propyline, right? So this is going to be my first thought process here, is that 1, 2, 3, that's one propyline unit. And 1, 2 here, that's going to have to come from another propyline. okay? So now, starting off here, I've worked out that there's one bond in my product that I know has to be formed, right? And that's this guy here. Well, how do we form carbon-carbon bonds? This is again where I'm talking about it really requires a bit of a mastery of what we've done up until now in order to know that we only have this one way of forming carbon-carbon double bonds, and that's using the acetylide ions, right? So what I'm going to think is, how do I form that bond there? Well, the only way that I have to form carbon-carbon double bonds is, again, using something like this and reacting it with something like this. Oops, sorry, this is an ion, right? And importantly, 1, 2, 3 carbons in that, and 1, 2, 3 carbons in that. And so if this were to react, oh, I'll go the other way, that would allow me to form a new carbon-carbon double bond, right? So this is, again, this idea of retrosynthesis, where, you know, they use kind of these big fat arrows to mean like, I don't know, it's kind of deceptive. I guess it should go the other way, but yeah, it means these would be formed from. So if I had this, I would know how to form that bond. Awesome. But now I have to figure out how to make each one of these, right? And I can only start with propylene. Well, do we know how to make, so let's take each one of these individually now. I'm going to get rid of this arrow just to be clear. How do we get from here to here, and how do we get from here to here? This is my next thought process. Well, I can get from here to here in this one in one step. And that is, I have to be able to add the anti-Markovnikov halogen. So this would be HBr in the presence of peroxide, right? So that would get me there, okay? What about in this one here? I'm actually gonna have to do a bit of a roundabout way. I'm gonna have to first, and this is where, again, it just helps to know all the different tools that we have, because I hopefully know that I can go first to add Br2, and I'm gonna be good and include our solvent. And this would create a dihalide. And then if I had this in the presence of that sodium amide, an excess of sodium amide, I would be able to create that acetylide ion. Okay, so what I'm gonna have to do is I'm gonna have to take my original source of propylene, and I'm gonna have to do I'm gonna have to split it up. I'm gonna take half of it and do one thing, where I first add liquid bromine. Oops, that's a 4. And then I'm going to add, so I'm going to just move my scratch work down here. And then I can add the sodium amide, an excess. And this will allow me to create my acetylide ion. And then the other half, I'm going to take and add HBr in the presence of peroxide, and that's going to get me my, my alkyl halide. So then I can combine these two, and what am I going to get? Here, I'm going to make sure I did this correctly by going 1, 2, 3, 4, 5, 6. All right, cool. And importantly, I guess I'll color code these in such a way, 1, 2, 3, 1, 2, 3, such a way that we can see who came from what, 1, 2, 3, 1, 2, 3. And so indeed here, is my new bond. All right, and then I'm not done there yet because I haven't gotten to hexane. How do I go from what would be 2-hexyne to hexane? Well, then I can just add, do a catalytic hydrogenation. Okay, so I know it seems like it's kind of like spaghetti logic here, and unfortunately that's the best that we can do. Look at your product and see what needs to be done. And then you got to think back to all the things that you know how to do, which I know sounds daunting, especially now because the material's so new. So the best thing that you can do is just practice, practice, practice. Do a bunch of different reactions. It's would be very, very helpful to just sit down and draw an alkyne and say, what can I do to this? I'm going to do this step. What can I do from here? Can I do this step? At some point, you're going to get to some product where you don't know what to do with. That's cool, but just play on pencil and paper with all these different reactions because they can be mixed and matched in a ton of different ways. And that's both the awesome part about chemistry, but from the standpoint of the student, the real pain in the neck part about chemistry. All right. And I am going to try my best through the design of the course, and in particular this week's challenge problem, to force you guys to practice, practice, practice your synthesis.